Okay. Is this the problem?
Yes, sir. I wasn't sure on what the function was going to be for this.
So it is a periodic function. You see,
Yeah.
it is given as t over here, the value from 0 to
Yes.
pi,
Yeah.
and from pi minus t from pi to 2 pi.
Yes, sir.
And it says it's a periodic function.
Yeah.
And since it's a periodic function and you have been given two different values over here, you can expect that the function repeats after 2 pi.
Yes. So after 2 pi, I'll get the value t again, and then when that reaches 3 pi, I'll start getting pi minus t again.
Correct. So basically your period is 2 pi.
Yeah.
And then you apply the periodic function Laplace transform, which is this. Where is it?
Okay, so in that case, I directly substitute ft as either t or pi minus t.
That's correct. So what happens is this t will be replaced by 2 pi. Okay.
Yeah.
And then this 0 to 2 pi, you will split up. 0 to pi and pi to 2 pi, you will split up into separate integrals. From 0 to pi, the ft value will change to t. And from pi to 2 pi, the ft value will change to pi minus t.
Okay, got it.
And then you have to solve it. Is that clear?
Yeah, I can do that on my own.
Okay, fine.
Yes.
What next?
So your voice is breaking a little.
1 second. Hold on. I'll just change my network. Just a second. Are you able to hear me?
Yes, sir.
Okay. So so we understood this particular problem. What next? Which next?
Yes,
which is your next out?
So 59.
Yes. Which problem?
So the first part.
Okay.
The first question. So I don't know why I couldn't do the previous one when I look at this now, but I solved the question, but I'm not getting the final correct answer.
Have you shared this picture with me?
Yes, sir.
Let me have a look. Okay. So that's on the third page, I believe.
Yes, sir.
P minus 1 plus 3 minus t plus 1 ut minus 2. Minus 2t. Okay, so now you have to find the Laplace transform. First of all, okay. See, you see there are two parts of the function in the in f of t. The first part is t minus 1.
Yes, sir.
Okay, and that t minus 1 part is actually an independent part. You do not need any kind of transformation in that. You directly apply the Laplace of t minus 1. Am I clear?
No, so I didn't get why that's the case.
Okay. Let's look at an example which will probably make sense to you. You see this?
Yes,
no, not this.
Yeah.
Let's look over here. You see this particular part? You are clear that the first part t square is written as it is?
Yes, sir.
And you apply the Laplace transform of t square directly.
Okay.
It's a linearity property. This
okay.
Laplace transform of this and Laplace transform of this and Laplace transform of this, you are separating them. Because of
but isn't that like in our question? Isn't that like our F1 and F2?
Yeah, that's what.
Yeah, so sir, in the formula, like in the I think second shifting method, it's called.
Yes.
Don't we have F1 like F2 minus F1 as a part of it?
Yeah, so F2 minus F1 is in the next bracket, right? The first bracket is t minus 1. Why are you changing that?
Okay, that part is got it. Okay, yeah, I understood what you're trying to say now.
That has
nothing to do with the.
Yeah, that has nothing to do with the second shifting property.
I got it.
Okay, so you have written over here t plus 2 minus 1, which is not correct because you substituted t by t plus 2.
Yeah, okay.
Okay, so that's the first mistake. The second is okay, let me come back to the equation. Yeah, so you have 4 minus 2t. Now, tell me one thing. Why did the... are you on that notebook? Are you on that page?
Yes, I have that page.
Okay, fine. So tell me one thing. It's the third step, okay? In the third step, okay, first of all, see, I'll tell you the mistakes. What you have done is, you have written f of t, okay?
Yes, sir.
You have, in the second step, you have written f of t again. Now tell me, the third step, what you have written, t plus 2 minus 1 plus 4 plus 2 into t plus 2. What is that? Is it f of t?
Substituting...
Is it f of t?
Sorry? Yeah, that's supposed to be f of t.
How is it f of t if you are substituting t by t plus 2?
Yeah, I realize that.
It's not f of t. So what you probably meant to do is, you were going to do Laplace of f of t, and then you would have, on the right hand side, it would have been Laplace of t minus 1 plus Laplace of 4 minus 2t into u of t minus 2.
Okay, so
and
that's
in the
two
next
separate
step, in the next step, Laplace of t minus 1, you would have split that even further. Laplace of t minus
t
Laplace
and
of
Laplace
1.
of minus 1.
Okay.
Yeah.
And then the third term over there, which is the heavy side function, you would have written Laplace of, instead of writing the entire thing, you would have written 4. Then there should be minus 2 into t plus 2. I'm not sure why there is a plus over there.
Minus 2 into t plus 2.
Is that a plus before 2
Okay.
or a minus?
Yeah, I think I put a plus.
Okay. I am not sure why that plus came. Because
Okay.
it's a minus
Yeah.
on the top.
Oh, right. Yeah, 4 minus 2t. Yes.
So it should have been 4 minus 2 into t plus 2.
Yeah.
Which would have been 4 minus 2t minus 4. So it would have been just minus 2t.
Yeah.
And then the Laplace transform of minus 2t would be minus 2 into 1 upon s square.
Yeah, 1 upon s square.
So minus 2 upon s square. Okay. That would have been that part. And t minus 1, t will be 1 upon s square. Whereas minus 1 would be minus 1 by s. So, okay, where does e raised to minus s come?
So e raised to minus s should be in the formula only, right?
Oh yeah, I forgot about this. Yeah, so e raised to minus s will also, not minus s actually. In this case, it will be e raised to minus 2s because you have t minus 2.
Yeah.
So e raised to minus 2s will come before the step of Laplace of 4 minus 2 into t plus 2. So you see, in your problem, you have never mentioned Laplace of f of t anywhere.
Yes, I saw that.
You have just mentioned f of
I
t.
took the whole thing as an equation.
Correct.
Yeah.
And in the end, you directly have e raised to minus 2s and that. You have not mentioned Laplace of f of t anywhere.
Yeah.
So that is why you need to have your LHS and RHS clear. If you're writing both, it is very good because you know what you're writing. Right now, what you're writing is only the RHS part. That's fine. But you are confusing with the steps.
Yes, sir.
Okay. This is probably one of the reasons why even though your answers match, you are not getting full marks.
Yeah.
Okay. There is a chance. I'm not saying that this is the reason, but I see that you're able to get to the answer, but I see steps missing, which is not clear while one is going to check. Is that clear?
Yes.
So whatever you are writing, whatever answers you have written so far, I don't mind you taking some extra time to go through that answer one by one. If you want, if you need help for that as well, I can take a separate class for that. Maybe I can tomorrow. I will schedule 1 hour just to help you with the answers, how it has to be written step by step. Okay, but that is an important thing to be taken care of.
Yes, sir.
Okay, fine. Any other doubt?
No, sir, not so far. Okay. Actually, sir, one more doubt. It was it was in the first class. This thing, I don't remember the slide number. It was this, but it was in like the first few slides. The question is basically sine of in brackets a plus bt.
12, 13, 18, 19. Let's see.
I think 12.
Not this.
No.
This one.
Yes, sir. First question here. Yeah, I was not able to do that.
Okay, sine of a plus bt. So do you know the formula for sine a plus b?
Sine a plus b, no.
Okay, so sine a plus b is sine a cos b plus cos a sine b. Is it not there in your trigonometric identity? Hello?
No, sir.
1 second.
Sine a plus b. Okay, I got it. Sine a cos b plus cos a sine b.
Yeah. Do you have it or you don't have it?
Okay, then I use the no, I just found it. Then I use the sine cos thing and cosine.
So in that,
like, sine a cos b becomes half of sine of
no, understand.
X plus y.
Understand. One second. So you say sine a into cos of bt plus cos a into sine of bt. Now sine a and cos a, these two terms are actually constants. So they come out of your Laplace transform, and then you do Laplace of cos bt and Laplace of sine bt.
Okay.
Laplace of cos bt is actually s upon s square plus b square.
Yeah.
And Laplace of sine bt is b upon s square plus b square.
Yeah.
And therefore you have s into sine a plus b into cos a upon s square plus b square.
Oh, okay. Yeah, I couldn't get that identity.
Is it clear?
Yeah.
Okay. Anything else?
No. So in that question only, if after I did the first identity and I got sine a cos b and cos a sine b, could I use the sine cos this thing like sine x cos y?
No, I did not understand.
So basically the second question I solved using the identity that sine of sine x into cos y is equal to half of sine x plus y plus sine x minus y.
I'll tell you the reason why over here splitting is important, and over here after splitting, this is a complex angle a plus bt, correct? But in this, a is a constant and bt is a variable.
Yes.
So when you're applying the Laplace transform, you are doing sine a cos bt plus cos a sine bt. Okay. But after you have done that, you are not going to apply the formula that you used over here.
Yes.
Because in that, the sin A and cos A are coming out of the Laplace transform, being a constant.
Okay.
In this particular problem, you have sin 3t and cos 2t where both are variables.
Yes.
And therefore, you need to split them before you can do the Laplace transform.
Okay.
That's why you use the identity that you're thinking of. You can apply it over here, but applying it over here again after splitting it does not make sense.
Okay.
Am I clear?
Yeah.
So the sin A cos A is actually a constant. Even though there's a trigonometric aspect to it, it's a constant.
Okay. Yes.
So you don't have to apply it or sin A cos bt. You do not apply the split on that particular term. You just remove sin A. Sin A,
Yeah.
you can keep it outside the Laplace transform, and you just have to apply Laplace transform to cos bt.
Yeah. So, but then what happens to the sin A and cos A?
The
Like
sin A
after
and
we've
cos,
taken it out?
it remains as it is, na? That's why sin A gets multiplied by the numerator of Laplace of cos bt. Laplace of cos bt was s upon s square plus b square. Therefore, s into sin A.
Yes, sir. Yeah. But then what about cos B?
No, it's cos bt, not cos b.
Sorry,
Laplace
cos A.
transform
Sorry.
of cos bt is s upon s square plus b square.
S upon, yeah. So, sir, if we take both the sine and the cos out, we have a linear term that we take the Laplace of, right? So we get two Laplace transforms.
Correct.
And sir, if we multiply the sine A by the first term, then what happens to the cos A?
The cos A is multiplied with the second term. That is the Laplace transform of
So-
sin bt.
Okay, so when we're taking it out, as in we're taking it out because, okay, so we're taking it out individually from each this thing as a constant,
One second.
not together.
Let me write it down. That will probably be easier for you to understand. Are you able to see the screen?
No, so I just got what it was. No, I'm not.
My screen is not visible.
No, sir. 1 minute. No, sir.
Okay. Stop presenting. Start presenting again. Yeah, is the Word document visible?
Yes, sir.
Okay. So you have
So I got to this thing.
the linearity.
Yeah, when you said we were taking them out, I for some reason assumed you were taking it as common and you were taking one term out. You were
No.
splitting it into two terms and then taking it out. Yeah, I just realized that when I was asking you the question.
So this is, I'll just write it down still.
Yes, sir.
This is what is happening. And
Yeah.
then what happens is you do Laplace transform of the first term plus Laplace transform of the second term. So it will be sin
Yeah.
A multiplied by Laplace transform of cos
Cos B.
bt. Sorry. And plus it will be cos A into Laplace transform of
Laplace
sin
transform.
B.
Sin B.
And now what happens is Laplace transform of cos bt is s upon s square plus b square. This becomes b upon s square plus b square. The denominator is the same.
So you can add the final term.
So you can add the numerators.
Numerators, yeah.
So this is
The
s into
denominator
sin A
remains the same.
and this is b into cos A. And that's what you get. Oh, sorry.
Yeah.
What is this? Close. And that's what you get over here. S into sin A plus b into cos A.
Yep.
Clear?
Yes, sir.
Okay. Shall we go to slide 60 now?
Yes, sir.
Okay, so this is where we start with inverse Laplace transforms. So inverse Laplace transforms is basically how you were able to relate the derivatives and the integration, correct?
Yeah.
You had a derivative formula and then you can use the derivative formula to get to an integration formula. Similarly, the Laplace transform formulas you have, I'm not sure if you have prepared a sheet for Laplace transform formulas yet, but based on those formulas, we will now get the inverse Laplace transforms. Okay?
Yeah.
Inverse is, okay, now I'm not sure. So if you have heard inverse in integers, so the inverse of 2 is half.
Yeah. More commonly trigonometry, but
Yeah, in trigonometry as well, like sine theta is x, so theta is sine inverse x.
yes.
So similar to that, over here you will have, if you know Laplace transform of ft is f of s, we can say Laplace inverse of f of s is f of t. And the inverse is written as raised to minus 1 to the Laplace transform operator, that is the capital letter L.
Yeah.
Okay. Again, the linearity
Yes.
property is applicable to the inverse Laplace as well. So if you have f1s and f2s in addition, okay, in addition or subtraction in the Laplace transforms, you can split them and do the inverse Laplace on f1s and f2s separately and get the final answer. Is it clear?
Yes, sir.
Okay. Let's move on to the next one. Inverse Laplace transform of standard functions. So we know Laplace transform of 1 is 1 over s.
Yeah.
So inverse Laplace transform of 1 over s becomes 1.
1.
Similarly, inverse Laplace transform of k over s becomes k.
Okay.
Okay, so that is just an example given over here. Inverse Laplace of 3 by s is 3, inverse Laplace of minus 7 upon s is minus 7. Now
Yes.
we know Laplace transform of e raised to at is 1 over s minus a. Laplace transform of e raised to minus at is 1 over s plus a. So similarly, inverse Laplace of 1 over s minus a is e raised to at. Inverse Laplace of 1 over s plus a is e raised to minus at. And these are the examples.
Yes.
S minus 2, since it is minus, you have a positive number in the power of
numerator. I mean the power.
Power, yeah, and since it is plus, it will be a negative 5 over here.
Negative 5. Yes, sir.
Now over here you have we know sine 80, Laplace transform of sine 80 is a upon s square plus a square, where a is a constant. Okay, so if you just have 1 over s square plus a square, this is as good as a upon a. So that upon a, that the a in the denominator remains as it is, and a upon s square plus a square inverse Laplace becomes sine 80, and therefore you have this. Is this clear?
Yes, sir.
Similarly, for cos 80, the Laplace transform is s upon s square plus a square, so inverse Laplace of this becomes cos 80. Is that clear?
Yeah.
These are the examples given. S square plus 9, if it is a constant, that means it has to be a sine function, and therefore you will see 9 is actually 3 square, so you'll write 1 by 3 sine 3t. Over here you have s square plus 5, so 5 is actually root 5 the whole square, and therefore you'll write 1 by root 5 sine root 5t. It is s upon s square plus 4. 4 is 2 square. You have an s in the numerator. It has to be a cos function, and you write it as cos 2t. Are the examples clear?
Yeah. So why does the sine 1 have a denominator?
You mean this, the number?
Yeah. Why is it 1 upon a sine 80?
Correct. You understand, for sine 80, the Laplace transform is a upon s square plus a square.
Oh, right. Okay.
But we
yeah,
do
yeah,
not have an a over here. So
yeah.
since
So
you
if
need
it was
an a,
upon, then
you will multiply a upon a. One a will remain in the inverse Laplace. The other a will come out in the answer.
got it. Yes, sir.
Is that clear? Okay.
Yeah.
Let's move on to the next slide. This is hyperbolic sine. Again, hyperbolic sine had an a in the numerator. It is not over here. Therefore, you will have it over here.
Yes.
Okay. S square minus a square, and this is s upon s square minus a square becomes hyperbolic cos 80. So similarly, you have 1 upon s square minus 3. 3 is actually root 3 square. So you have 1 by root 3 hyperbolic sine root 3t. This s square minus 5. S in the numerator makes it an hyperbolic cos function. Root 5 the whole square. Hyperbolic cos root 5t. Clear?
Yes, sir.
Okay. Now this one looks a little bit tricky. So let's focus on what we know. What is the Laplace transform of t raised to n?
N factorial upon s to the power n plus 1.
That's correct. So what would be the Laplace transform of t raised to n minus 1?
T raised to n minus 1. S to the power n?
No. Laplace transform. So you have what comes in the numerator first?
Oh, okay. I'm sorry. So my function is t raised to
Power n
n to
minus
the power
1.
minus 1. Okay.
Power
So
is n
in
minus
that case, I would have. Yeah, in that case, I would have n minus 1 factorial upon s to the power n minus 1 plus 1. So s to the power n basically.
Correct. So you have an n minus 1 factorial in the numerator, which is a constant, and you have s raised to
Yes.
n in the denominator. So
Yes.
over here, now you're doing an inverse Laplace of 1 upon s raised to n. Now, because you have a constant over here, the n minus 1 factorial is missing. You divide by n minus 1 factorial, and the numerator is
Okay.
t raised to n minus 1.
Okay.
And over here, n is a positive integer.
So how come it's minus 1 and not plus 1?
So we did right now, right? We did t raised to n minus 1.
No. I meant for, the top part. Oh, okay. Sorry. Yeah, that was the function we took.
That was the Laplace function. So now we are doing the
Yeah.
inverse Laplace.
Inverse of the. Yeah, got it.
Is it clear?
Yeah.
Okay. And this is the example. S raised to 4, you do 4 minus 1 upon 4 minus 3, 4 minus 1 factorial. Therefore, t cube upon 3 factorial, t cube by 6.
Yeah.
Okay. One change, if instead of an integer, you have a real number, then in that case, if you remember, in the Laplace transform of t raised to n, where n is not an integer, instead of a factorial, you had a gamma function.
Gamma function. Yeah.
That is what has come in the inverse Laplace over here now, if n is not an integer but a real number.
Yes.
Okay. See, gamma n, if it is an integer, we know it is same as n minus 1 factorial.
Yes.
Correct. So these two are the same things, but this becomes this if it is a positive integer.
Only if it's an integer.
Yes. Yeah. Okay. So is this clear?
Yes, sir.
Okay. Let's proceed further. Now we'll look at some examples. Find the inverse Laplace transform of 2 over s plus 3 plus 5s over s square plus 9. Now over here we can, first of all, you can use the linearity property. So 2 over s plus 3 will be separate, 5s over s square plus 9 will be separate. So you can do that separation. Now you can take out the constant as well. So 2 comes out over here.
2 and 5.
Okay, and 5 comes out over here. Now you look at the individual inverse Laplace transforms. So 1 over s plus 3, what happens? It becomes the power of e.
Yeah. So e to the power.
It will be
minus 3t.
Yeah, it will be minus 3t. That's correct, as mentioned over here. And similarly, now over here you have an s in the numerator, so it has to be a cos function with a plus sign. It is 3 square, so it becomes cos 3t, and therefore you have your answer 2 into e raised to minus 3t plus 5 into cos 3t.
Yes.
Okay, that's your answer. Let's move on to the next one. Again, a problem given over here. It is s plus 1 upon s raised to 4 by 3. Now, looking at this particular problem, you will feel that you have not come across any such problem. But what you can do is you can split the numerator. So it becomes s upon s raised to 4 by 3 and 1 upon s raised to 4 by 3. Now this is s power 1.
Yes.
Which means you can subtract 1 in the power in the denominator and becomes 1 upon s raised to 1 by 3.
Yes.
And this becomes 1 upon s raised to 4 by 3. Now this is where you have the power as a fraction.
So gamma function.
So you will use the gamma function. In the numerator you'll have the power of t, and in the denominator you'll have the power of gamma function. Now again, over here you have this function as well. I'm not sure if you know this. Gamma n is n minus 1 into gamma n minus 1.
Yeah.
So gamma 4 by 3 is written as gamma 1 by 3 plus 1, which is 1 by 3 into gamma 1 by 3, and this can be substituted over here, and that is what they have done. They have substituted gamma 4 by 3, and now you have a common denominator, so it becomes easier to make a single numerator with a common denominator.
So I can leave it in like gamma those things, right?
I would recommend like you can leave it over here, okay? But depending on how many marks are given, like if it is a 5-mark problem, they will probably expect that you merge the numerator as well. So t raised to minus 2 by 3 plus 3 into t raised to 1 by 3 and the whole upon gamma 1 by 3.
Okay.
Okay, like I was expecting one more step below this.
Yeah.
But they did not put it. Okay, shall we move on to the next one?
Yes, sir.
Okay. Inverse Laplace transform of 2s minus 5 upon 4s square plus 25. Okay. So obviously, so far whatever problems we have done, we have seen that we do not have any coefficient to s square, which means we will have to remove the coefficient of s square before we can apply any inverse Laplace transform. Okay. And whatever we are removing, obviously it will come out of the the outside the inverse Laplace. So the constant will come out.
Yeah.
And yes, so what they have done is they have taken 4 common. They have separated the numerator because you want the s term separate and the constant term separate. After you have done that, this becomes, so it was 2s, 2 and 4 come out. So it has become half over here. Correct?
Yeah.
Then s upon s square plus 5 by 2 the whole square. It is a plus in the denominator and it is s in the numerator. So this has to be a cos function. In the other side, you have 5 by 4 coming out. You have a constant on top and a plus sign. So this will be a sine function with the constant coming in the denominator separately. So it will be half into this becomes cos phi t by 2. Cos phi t by 2. And this will be minus 5 by 4 into 1 over 5 by 2 into sine of phi t by 2.
Yeah, 1 upon a into sine a.
Yes. So this will get 2 by 5 and 5 will get cancelled 2 by 4. This will become half. Half is common. Cos phi t by 2 minus sine phi t by 2.
Yep.
That's your answer. Is that clear?
Yes, sir.
Okay. Now, similar to the shifting properties we had in the Laplace transform, we also have shifting property in the inverse Laplace transform. That's correct. So if you have, say, Laplace transform of inverse Laplace transform f of s equal to f of t, then if in case you come across inverse Laplace of f of s minus a, you can simply, instead of s minus a, you can write it as e raised to at and inverse Laplace of f of s, which becomes e raised to at f of s. That's for s minus a. Similarly, for s plus a, it will be e raised to minus at into f of t. Is the shifting property clear?
Yes, sir.
Okay, it is the same thing that you had as the first shifting property.
Yeah.
Correct? Do you remember which page it was? The first shifting property?
I think after slide 13, maybe slide 14.
Oh, so early, is it?
Yeah, I think first shifting is like one of the first things we did, even before multiplying and.
Yeah, this one. Slide 14.
Yeah.
Okay, so this was L of ft is equal to f of s. L of e raised to at ft is f of s minus a. So it's the same thing you are doing inverse Laplace. Is that clear?
Yeah.
Okay, so that's your shifting property. Let's move on to some problems. So you have inverse Laplace transform of s upon s minus 3 raised to 5. So s minus 3 raised to 5. So we are writing it in terms of s minus 3 so that we can use the shifting property. Since you have written it as a function of s minus 3, you will multiply it e raised to 3t. Okay, and s minus 3 will be replaced by s. So it becomes s plus 3 upon s raised to 5. And e raised to 3t into s upon s raised to 5 will be written separately. 3 upon s raised to 5 will be written separately. The Laplace transforms will be done. The inverse Laplace transforms will be done. And 1 upon s raised to 4 becomes t cube upon 3 factorial. 1 upon s raised to 4
Yes.
becomes t raised to 4 upon 4 factorial. And therefore, you get this as your final answer.
So after we make all the s terms in s minus a, we just ignore the a completely because that goes for our e part.
Correct.
And then we just do Laplace inverse of whatever's left.
Correct. So s minus a, wherever there is an s, you see to it that it is written as s minus a term. Okay.
Yeah.
The other thing which is possible is, like, you remember you did the Heaviside function?
Yes, sir.
Where instead of writing everything as t minus a, you replaced t by t plus a.
Yes, sir.
So what you could do is, like, instead of writing s minus 3 plus 3, you just write s as s plus 3.
Oh, okay. Got
And
it.
over here also you write s as s plus 3. You get s plus 3 minus 3,
And then,
which is s.
okay.
Does that make sense?
Yeah.
Okay, but you have to do it everywhere. You cannot skip things.
Got it. So each and every s in that this thing has to be replaced with s plus 3 if I'm doing it.
And you can only have one number that you're replacing with. So just imagine, over here you have s minus 3, over here you have s minus 8, and you have another term s minus 10. You have to decide which is the shifting number that you're using. You
Okay.
cannot have different shifting numbers in a single inverse Laplace.
Okay. So, but sir, in that case, I can take any one of the numbers and solve the question?
No, you can't, because that will create issues. Okay.
Yeah, because e will have a different power with the number I take.
Correct. So you cannot choose. Okay, so if your Laplace transforms are separated already, then you can probably have a different shifting for each one of them. But if it is together, then you'll have to decide one of them. And most probably, like, if in case, just imagine this was s minus 8. Okay, just imagine.
Yeah.
In that case, I would still go with s minus 3 for the shifting, because this has a power.
Okay.
Okay, and s minus 8 in the numerator having no power, I can simply split it.
Into two linear terms.
Correct.
Yeah.
So I don't mind having another constant in the numerator, but I cannot have a constant inside the power.
Yes.
Okay, is that clear?
Yeah, got it, sir.
Okay, so you are clear with, you can simply do s to s plus 3. You'll still get it, but you have to note that it is done with every s inside the Laplace inverse Laplace transform, and you can use only one shifting within a single inverse Laplace. You cannot do multiple of them.
Yes.
Okay.
Yes, sir.
Okay, so now you have done this. You have just split it and you have applied, and you get your final answer. Is that clear?
Yes, sir.
Okay, let's proceed. So far, there is no homework for you, as it seems. we are doing the solutions for each and every problem. Okay. So today's target is actually.
And I don't know why, but inverse feels much easier also.
I
Maybe
would say,
because we're doing very basic stuff right now.
yeah, we are doing basic stuff, and more importantly, you have already done Laplace transforms. So
Yeah.
the inverse will not be that difficult.
Yes.
It's like how do I put it? I'm not sure. Like, once you know addition, subtraction doesn't feel difficult. Once you know multiplication, division doesn't feel difficult. It's something similar.
Yeah.
Anyways, inverse Laplace of s plus 3 upon s square minus 4s plus 13. Now over here, s square minus 4s plus 13. So what they have done is, they have tried to convert this as
Make it into a
complete square.
quadratic, right? Yeah.
Correct. So a complete square. And so with the 4s, I need actually a plus 4 to complete the square. Correct?
Yes.
So plus 4
Yep.
minus 4, and therefore you are left with s minus 2 the whole square plus 9.
9.
Okay.
Yeah.
Again, over here you see the numerator has s plus 3, but I have an s minus 2 inside the square. So my shifting will happen with this number.
S minus 2.
Correct.
So if I'm replacing s, I do s plus 2 everywhere.
Correct. If you are replacing s, you do you put s plus 2 everywhere, and that is how your shifting will complete. And you can check that over here again if you want. What has happened is s minus 2, so you have an e raised to, since it is minus, you have a plus, so e raised to 2t is coming out, and this is what you get at the end. So just imagine,
yes.
Over here you are putting s as s plus 2. So what becomes the numerator?
Sorry, I'm putting that will become s plus 5.
Which is what you get over here.
Yeah.
And over here, if you put s as s plus 2, it becomes s square plus
9.
Which is what you have over here.
Yeah.
Okay, so you have s plus 5 upon s square plus 9 on, and now you can just split them. It is a plus with an s, so it is a cost function. It's a plus with a constant. The constant will go out, and it will be a sine function in the inverse Laplace. And that's how you have solved your question. Okay?
Yes, sir.
Let's move on. This is your first slide for homework, slide number 74. I will make a note of it. Shall we go ahead?
Yes, sir.
Okay, so now we have come to inverse Laplace of e raised to minus as f of s. So we can look at Heaviside shift theorem. So we already had Heaviside shift theorem in the Laplace transform. Now we are seeing how we can use the Heaviside shift theorem for application in the inverse Laplace part. Okay.
Yeah. So this is the second shift, right?
Yeah, that's the
For t
second
minus
shift.
a. Yeah.
That's correct. So Laplace of f of t minus a into u of t minus a was e raised to minus as Laplace of f of ft. Okay. Then
Yeah.
the reverse way would be inverse Laplace of e raised to minus as f of s is f of t minus a into Heaviside u of t minus a.
Yes, sir.
Is that clear?
Yeah.
So let's look at a solution. You have inverse Laplace of 1 minus e raised to minus 3s upon s square. It's a simple linearity again. So 1
Yeah.
minus e raised to minus 3s, so you can just split it 1 upon s square with minus sign out, e raised to minus 3s upon s square. Over here, the first term is very straightforward. Correct? 1 upon s
Yeah.
square, we know it is s raised to n. S raised to n is t raised to n minus 1 upon n minus 1 factorial. So this becomes t upon 1. T, basically t.
Yeah.
Okay, this becomes t. Now, if you look at this, you have an e raised to minus as. Correct?
Yeah.
So that means the number 3 will become your shifting, Heaviside shifting
Yes.
value a.
That will become a.
Correct. That will become a. And therefore, you'll write f of t minus a into u of t minus a. Okay. How does this work? So in the f of s part, okay, what is f of s
Yeah.
for this function? 1 upon s square.
For 1 upon s square, that'll be t.
Yeah, 1 upon s square is the f of s, and therefore f of t is t.
Yeah.
And now, since f of t is t, f of t minus a becomes t minus 3
Yes.
into u of t minus 3.
Yep.
Is this clear? Is the solution clear?
Yes. Yeah, I got that.
Okay. Again, like coming from this point to this point, they have actually skipped a couple of steps where they could have mentioned f of s is 1 by s square. Laplace inform of f of s is f of t, which is t, and therefore f of t minus a becomes t minus 3. That is what was expected. So they have not done this part separately, but since the 1 by s square is common, they have mentioned it directly over here.
Yeah.
Okay, but had it been separate, it was expected you would write it separately. Anyways.
Got it.
Okay, so the solution clear? Any doubts?
No.
Okay, let's proceed. Laplace inform of inverse Laplace of e raised to minus 5s upon s minus 2 the whole square. Now s minus 2 raised to 4. You will see over here you have this. You also have this. Okay, you are having two separate things together. So this is basically
Yes.
you are having your first shifting and second shifting together.
Okay. Yeah.
Correct?
Yes.
So first you will do. So you have to decide which shifting to be done first. Obviously, your first step will be to do the second shifting,
First
the
shifting.
Heaviside shifting.
Okay.
Okay.
Yeah.
Because you need to remove this first
Yes.
before you can apply any Laplace transforms. So if you are going to remove this, you know you have to apply the formula for 1 upon s minus 2 raised to 4.
Yeah.
Now for this, you know it is Laplace transform of this, but you cannot apply this directly. So now you apply the first shifting for inverse Laplace.
Okay.
Okay, and therefore this 2 will come out positive e raised to 2t. Then you have Laplace inverse of 1 upon s raised to 4. S raised to 4 becomes t cube upon 3 factorial, which is 6. Correct?
I'm a little lost.
Where? On this step? Which step you are lost?
No, I got to the part where we did the second shifting.
Second shifting is this. You just second shifting, you know that e raised to minus as, okay, will
Yes.
be left out by converting f of t to this.
Yeah.
If it is only inverse Laplace of f of s, then it is f of t.
Yes.
But if it is inverse Laplace of e raised to minus as multiplied by f of s, instead of f of t, it becomes f of t minus a into u of t minus a. Now, you haven't reached this particular step yet. This is just the formula mentioned over here. They are first deciding what is f of t. Okay. So for f of t, you know your a is 5. Okay.
Yeah.
You know f of s is actually 1 over s minus 2 raised to 4.
Yes, because okay, yeah.
So to find f of t, you are going to do Laplace inverse of this, which is Laplace inverse of this. And now over here, to do this Laplace inverse, you have to do the first shifting. So this 2 becomes e raised to 2t, and this s minus 2 becomes
got
s. And now 1 upon s raised to 4, the inverse Laplace is t cube upon 3 factorial, which is t cube upon 6.
Okay, I just didn't get that t cube upon 6 part.
S raised to 4.
How do we? Oh, okay, we're doing the t to the power n thing.
Yeah, s raised to n is t to the power n minus 1 upon n minus 1 factorial.
Yes. Okay, got it.
Okay. So you got f of t over here.
Yeah.
Now This is f of t, but what do you want?
F of t minus a
Where
into
a
u into
is
t minus a.
where a is
5.
So within this f of t, you are now substituting every t with t minus a.
Yeah.
Okay. So you get
Yes.
e raised to 2 into t minus 5.
Yeah.
T cube becomes t minus 5 the whole cube. 6 remains as it is, and then it is multiplied by ut minus 5.
U. Yeah.
Okay. You don't have to simplify this further.
Okay.
Is that clear?
Yeah. So in our first, in like the heavy
Heavy
the
side
second shifting thing, we have a is equal. Yeah, heavy side shifting, we have a is equal to 5.
Correct.
But when we're doing the first shifting thing, our value of a is plus 2.
Correct.
Okay. So after we finish the first shifting to get the value of ft,
Correct.
we replace that value. We replace the
t by t minus
a value. Yeah.
That's correct.
Yeah. Okay.
Little bit heavy.
No, I got it. I mean, it took a little this thing, but I understand.
Okay, fine. Shall we proceed?
Yes, sir.
What I want you to do is, before you start working on the homework problems, you already have the
Solve
slides.
this.
Just go through these steps again.
Okay, sir.
Okay. Now we are doing it like, see, I understand I'm teaching you over here. We are going to it step by step, but it is possible that when you are going from one step to another step, you feel, okay, I am not able to connect them. If you are feeling any such things, you can just click a picture. You can message me saying that I'm not able to connect these two things, and I can help you. Like I can message you, or I can send you an audio saying that, okay, so this is how it works, so that you are able to at least proceed further.
Yeah, I got it.
Yeah, let's proceed. Let's go on to the next slide. Inverse Laplace transform of a derivative. Okay. Now, I think we already had Laplace transform. Laplace transform to get.
We had Laplace transform of an integral, I think.
Of an integral, is it? I don't remember.
Yeah.
We did not have for a derivative.
I don't remember. I'll just check quickly.
I'll also have to check because I don't. Yeah. We have this Laplace transform of derivatives.
Yeah.
And we also had Laplace transform of integrals. We had both.
Yes. We had both.
Yeah. But we are going to use one of these. Now I have to check which one are we using. Let's move on to that particular page. Derivative. Okay. So we are not using that actually. This is separate is what I can say, because we already know inverse Laplace of f of s is f of t.
Yeah.
In that case, since we already know this, okay, in that case, the inverse Laplace of the nth derivative of f of s, okay, becomes minus 1 raised to n into t raised to n into inverse Laplace of f of s.
Okay.
Okay. Only when we know this, we can actually do this. Okay. That means we should know the integral of this. If we know the integral of this, that is where we can come to f of s.
Right.
It is not a single integral. Okay. It is the integral of n times. If we know this, that is when we can apply this. Okay. Let's look at an example. If we have one. No, we don't. It might be hard. Let's look at the next step. Inverse Laplace transform of a logarithmic and inverse trigonometric function. So if Laplace is f of s, then Laplace of pft is negative derivative of f of s. Now this is what we already know, I believe. Do we know this? This was the t property, right?
A t into f, multiplication by t.
Multiplication by t property. What page was that? No, it was a division by t actually. But multiply by
we had both
to n.
Multiplication and divide.
Yeah, multiplication by t raised
t raised to n.
Correct.
Yeah.
So multiplication,
that's around slide 20 and
so
division is on slide 30.
Yeah. So this is minus 1 raised to n. So the same property they have mentioned on page 79 now, which becomes minus 1 raised to n is minus 1 because you are doing only the first power of t, the first derivative of f of s. And so you can do the reverse, that is the inverse Laplace of the negative derivative is same as t into f of t, which is inverse Laplace of f of s. Is that clear?
Yeah.
Basically, this is the proof, I would say.
Yeah.
Is this the proof? That's how you are getting this power of t and the negative sign.
Yeah.
Is it clear?
Yes, sir.
Okay, let's look at the problem. Inverse Laplace of log of s plus a upon s plus b. Now, because it is log of s plus a upon s plus b, they can be written as this: log of s plus a minus log of s plus b. We can do the derivative of this. The derivative of the the negative derivative will be minus 1 upon s plus a plus 1 upon s plus b. The inverse Laplace of this is minus L minus Laplace inverse of 1 upon s plus a. 1 upon s plus a becomes e raised to minus at, and 1 upon s plus b becomes e raised to minus bt. So this becomes e raised to minus bt minus e raised to minus at, and we know the formula of this is actually t into f of t.
Yeah.
Okay, and therefore, since we are looking at f of, we want to find f of t, we will divide both sides by t.
We divide by t.
And that is how you get to your answer.
Yes.
So the use is basically, if you are not able to apply directly the inverse Laplace, you can differentiate it and then apply the inverse Laplace to get to your answer.
Yeah.
Does that make sense?
Yes, sir.
Let's proceed to the next problem. Inverse Laplace of tan inverse a by s. Again, tan inverse a by s, it's an inverse trigonometric function, and we do not have a direct formula, so we have differentiated it. The negative differentiation, which makes it a by s square plus a square. Tan inverse derivative, is it positive or negative?
I think it's negative.
Are you sure?
I'll just check.
Yeah, just check. I feel that there is, the tan inverse derivative shouldn't be negative.
No, it's given as 1 upon 1 plus x square. So in this case, it should be a upon a plus s square. It should be positive, basically.
Yeah.
So with the negative sign.
Yeah, it has to be a negative sign, right?
Yeah.
Okay. Yeah, correct. 1 second. 1 second. No. You over here, s is in the denominator.
Yeah, so we're differentiating by s, right? So
yeah, but
it comes to the same. Oh, okay. S is in the denominator. Got it. Yeah.
Yeah, so it's not the same.
Got it. Yeah.
So that's why the negative
sign. So in this case, it's tan inverse 1 upon x.
A by s. A by s is actually. So it will be 1 plus x square, but x becomes a by s, and the s square will get cancelled, and the negative sign will also get cancelled. Okay, fine. Okay, so this is correct actually. They have skipped the steps, and that's why it is. That's why we have to verify whether it's correct or not. You're clear why it is clear? Why this is correct?
Yes, sir.
Okay, so you have 1 upon 1 plus a by s the whole square, and then you have the derivative of a by s as well, which is a into minus 1 upon s square.
Yeah.
And therefore that s square gets multiplied throughout. The negative sign gets multiplied by the negative and becomes positive, and therefore you have this entire thing as positive. And therefore you have the Laplace inverse of this is simply sin 80, because this you already have a constant a over here, so you don't need a 1 by a, correct? And it becomes sin 80, and this is actually t ft, so ft becomes sin 80 by t. Is this solution clear?
Yes, sir.
Let's proceed. Page number 82 is homework. How many problems? 4 over here, and 74 was also there. 4 over here. So 8 problems so far. Division by s. Okay, so if you know the Laplace inverse of f of s is f of t, then the Laplace inverse of f of s by s becomes the integral, closed integral 0 to t f of t dt. It should not have been f of t dt, it should have been f of u du. Okay?
Yeah.
Just have a look. Just look at a reference book if you have. I think you should not be having t over here, because the variable cannot be the limit. Is that clear?
So what do I have to look for?
I think this cannot be t. This has to be written as f of u du.
Okay.
I think page 39. See, this was over here. If you see, right, you have f of u du. You do not write it as f of t dt when t is in the limits.
Yes.
Okay, so that's why I feel that thing is not written correctly. It should have been f of u du. Okay, but you understood what's happening over here.
Yes, sir.
Okay, and now we come to this particular. This is the last slide for today. Inverse Laplace of 1 upon s into s square plus a square. Now you have an s over here. You're dividing by s, so you can simply use this particular formula and write it as integral 0 to t f of t dt. Now f of t in this particular case will be inverse Laplace of 1 over s square plus a square, which is 1 by a sin 80. So 1 by a is a constant. It comes out integral 0 to t. Instead of sin 80 dt, you should write sin au du preferably, and then integral of sin is minus cos. So minus cos au from 0 to t. If you put t first, it will be negative cos 80 and negative minus of minus cos 0. Minus of minus, sorry, yeah, minus of minus cos 0.
Yeah.
Cos 0 is
That's
1.
plus 1.
So minus of minus plus 1. So 1 minus cos 80. And there will be an a square. Sorry, I forgot about the a square because you have an 80 over here. After integration, you'll have another 1 upon a coming up. So 1 by a square.